see it right now, right?
Perfect. Looks beautiful.
Yeah, thank you.
Let's go.
Okay, let's go. Let's go to. I know it has been a long day, right? So let's try and be rather quicker and not use all of the hour. Okay, so welcome to this session. So last time we were talking about boundary conditions. To remind you, I think everyone knows me already, but I am Guillermo Giraldo. I'm FEA specialist, independent consultant, and also support agent at SimSkill, where we provide simulation software in the cloud. So today, for a more practical application, I wanted to go over a little example. It's a simple example, but it's a nonlinear analysis nonetheless, with all of the nonlinearities we will see in a while. And I wanted to showcase this little tool, or it's not a little tool, it's a really very complete tool. It's under development, features coming all the time. I don't know the author of this tool, but yeah, I want to congratulate him. It's a wonderful tool. I did, and I hope that it keeps growing and it keeps getting more users, which is what one wants, right? So this tool is PrePomax. So PrePomax is a pre and post processor for the Calculix FEA solver. Calculix is a very, very popular solver, but it doesn't have a dedicated preprocessor to set up all the cases and post-processor to check the results. You have to use Gmesh or Salome Mecha to build the geometries and the meshes. Still in PrePomax, you cannot build the geometries, but you can mesh most of it, and you can have great meshes as the one I have created here. You can also use Salome Mecha to run Calculix and everything, but I think this is a really good alternative. And for many, many cases, I think it's very well deserved to be considered for your projects, both academic and I think professional. I mean, there is no issue with professional. Can we model composite materials in Calculix? I think yes. I haven't done it. Giuseppe? I think I haven't done it, but you have the option to mesh shells here in PrePomax. I think not yet the option to define composites. So I'm not sure if you need to manually edit the input file for Calculix, but I think it's possible. And if not possible, then I guess you can resort to Codaster. So let's get into the example. So I was modeling this example, which is a lock with a pin that is pushing. You can see here the depiction of the boundary conditions, and I'm pushing it under a uniaxial tension stress. The contact between the pin and the hole is a physical contact, which means it's not bonded, so it can slide, and it also can separate, which gives us a very realistic condition on the stress results. And it's a very simple model. It's fixed at the back, and we are applying this force to the pin. The pin is modeled as a rigid body. So you can see here the depiction of the remote point at the center, and I am applying the force directly on the center and in the x direction. You can see in the red x direction, and then I am constraining all the other degrees of freedom on the remote point. So I have a purely horizontal or uniaxial results, displacement in the results. Let's check the results quickly. Okay, so you can see here the displacement on the red part. It's very small displacement, 0.2 millimeters, if I'm not counting wrongly. So let's check the von Mises stress. This is on the last step. You can see the von Mises stress distribution. We can also see the plastic strain. So we can see the regions where plasticity is happening. I can select this part and hide it, so we can focus on we can see the stress distribution here and the maximum values on the whole. So these are my results. I can, for example, let's show this again, and we can see the small clearance that is created here. Initially, all these parts, these phases were coinciding. So we can see that the physical contact is working. And if we want to see an exaggerated, so let's see, exaggerated deformation, I can put a factor here of 10, and you can see how it grows. I can make it 100. Now it's very realistic, but you can see like an exaggerated, the ovalization of the whole. Okay, so what I want to do right now, and we'll go through it step by step, is to perform two things. You can see there is also a little bit of a side deformation here that it's visible when exaggerated. But what I want to do here is two things. So the first one, you can see the lateral deformation, and I want it to be a purely uniaxial case. So for that, we will implement a little bit of what we talked about on the last session, is to leverage the symmetries in the system. So we can see that if we go back to our model, we can see we have a symmetry plane normal to C, and we have a symmetry plane normal to Y. So if we cut it, we will model a quarter of the geometry, right? That will help us to have a uniaxial state that is not disturbed by the imperfections in the mesh. So I don't need to mesh so fine to get rid of it. Also, it will save a little bit of computational time. And the other thing that I wanted to that I wanted to perform here, is that on the plastic material, I use the engineering values for this material. And I wanted to do an improvement, which is a correction to move to the true stress strain values, which is always recommended when performing plasticity simulations. So let's do this. Here you can see that I have my Salome program with my quarter geometry. As you can see, here is the original geometry, the full. So I just performed a couple of cuts and took just the quarter. So what I'm gonna do right now is to export this geometry. So the quarter geometry, export, let's use brep. So let's call it quarter and save. My units is in meters. I can check, for example, my bounding box, and you can see that my bounding box is 0.3, 0.1, so it's in meters. Okay, so now that I exported my geometry, so I'm gonna save this and put it on the side. And let's open a new PrePomax window. I don't want to recover an old session. And let's start. So first I will open a new model, 3D, and my units are in meters. Okay, so I have to be consistent, but it helps me with the units, which is very nice. In general, FEA solvers do not have any information about units, so it's nice to have a processor or a companion that helps you be checking with units and reminding you of the units of each one of the quantities that you input. So, okay, so now I have my model ready, and I'm gonna import my quarter geometry. So it's a compound, you can see, and I can check by the ruler that the scale is okay. So I don't have like it interpreting that it is millimeters and having huge, kilometer big parts. I'm gonna do a quick renaming. So I'm gonna call this the plate, and I'm gonna call this pin. So I have my two. Now let's go to the meshing parameters for the compound part. Let's do something here. Let's continue. So my meshing parameters, for my maximum element size, I want, say, 5 millimeters. And for my minimum, I want 1 millimeter. Second order, yes. I can click the little icon and it will preview, that I will have at least 2 elements across the thickness. And that would say okay. And let's say please mesh. And this is the mesh that I have. You can see that I didn't have the 2 elements that I wanted. So I can go back. In the refinements in the max element size, let's say 2. Too much. That's right. Ooh, maybe too much, right? Let's wait for it to finish. It looks better. Okay, let's use it. So it brings me automatically to the model setup. Now I can go just down the line and fill all that I need to fill here. So the first thing that I will create are my surfaces sets for my physical contact. So I want my master to be the surface of the pin, right? Because that's, or it can be anywhere. I will just pick the master one. Okay, and create a new one, which will be the slave. I can hide the pin to select the face of the hole.
Guillermo, for those who are not familiar with master slave, could you quickly explain what that means?
Yes. So we will go to it in a moment, but yes, for sure. When we define a physical contact, like the one I showed you, the interaction between the surface of the pin and the surface of the hole, we need to define, one surface and the other surface, the two sets of surfaces that are in contact. The way the algorithm works, it needs one to be master and one to be a slave, which means that the position of the slave is compared against the master, and then a numerical scheme is applied for it to make it conform, to make the physical contact work, which means that is to avoid the interpenetrations between the master and the slave surfaces. That's how, in general, how physical contact works. So we will check in a moment and we will assign it and see how it works. The next point, the next thing is a reference point. So what I will do here to help me a little bit with the stability is that as I am interested more in the stresses of the hole, and I am assuming that the pin is rigid, I'm going to create what is called a rigid body. So in order to create a rigid body, we create the body will work as a rigid body. It can deform, and it will only have the 6 basic degrees of freedom. So it can displace in the 3 coordinate directions, but it can also rotate. So in order to specify this, I need to first specify a remote point, which will be the center from which I will control the rotations and the displacements. So I will create such point right now, and then we will connect it to all the nodes or in the volume of the pin, and then it will create as a rigid body. So let's create this point right now on the reference points. I'll call it RP1, and the coordinates 0, 0, 0 are okay for me, which is on the center of the original pin, not the quartet geometry of the original. You can see that I can also select the location from coordinates, but it's okay from a node point. So I have now my reference point. Next, walking down the line, I will create my materials. So I just double click here, and I will create a linear or an elastic material. I double click here, and I can enter the elastic properties. I will enter the properties of a steel, which is a Young's modulus of 200 gigapascals and a Poisson ratio of 0.3. And that's all I need for the moment for this elastic material. For the plastic material, I'm gonna call it plastic. I need the elastic properties, which will be the same, 200 gigapascals, 0.3 Poisson's ratio, and then I add the plastic properties. You can see that it takes me immediately to this table. So in this table, as for the yield stress versus the plastic strain. So I have a little Excel here. So these are the properties that I used before, which are the engineering properties for this material. So I have 3 points, so the 0,0 point, so 0 stress, 0 strain. I have my yield point at 150 megapascals with an strain of 0.02. And then I have a ultimate point, which is 300 megapascals with 0.3 of a strain. If I plot this, you can see that it plotted it in a weird way, right? Okay, because it's swapped. Sorry. Let's do it the other way around, and I can, for example, move this. Oh, sorry, it's so bad. Okay, let's obviate this for now, just to not burn time. But what I want to do, and the first thing one of the things that I mentioned, is that it's recommended to convert the engineering stress and strain into true stress strain values, right? So you can search for the equation for this, but basically the equation for the true stress is 1 plus the strain times the original stress. And the equation for the strain is the natural logarithm of 1 plus the strain. So if I apply this, you can see that I have quite different values. So let's compare. So on my yield point on engineering stress, I had 150 megapascals, and here I have 150 megapascals also. So it didn't change too much. And the strain also didn't change too much. But you can see that on a point with high strain, say on the ultimate point, we can see the difference. So from 300, my ultimate true stress is now 390 megapascals. In my strain, which was 0.3, is now 0.262. So it's lower. It's lower. And because of the way that the finite element solvers work, these values are preferred. So let's enter these values. I'm gonna put it here on the side, and let's enter them manually. Oh, sorry. The second thing that you will notice here is that it is requesting for plastic strain. So it's not the total strain that we need to enter, but we need to enter the plastic strain. And the first point should be the yield point. So this first point, we won't add it, right? And in this point, the plastic strain is the strain of the total strain, so the true strain, minus the strain at the yield point. So what I can do is this value minus, say, this value. So the first point is 0 for yield, but if I compute it for the other one, then I have a little bit of a difference, 0.26 instead of 0.262. So we are only entering the plastic region of the curve and not the elastic region. That's the way PrePomax works. So very important when you are using a new tool to be aware of what it is asking. Otherwise, you will have bad results, or you won't even have results. So the yield stress is 150 megapascal, and the plastic strain is 0. And at my ultimate point is 390, and my 0.26 strain. So these are my true values. And this is a bilinear curve. Let's do something here, because I don't want the curve to end at here. Something that is commonly do in the trilinear curve is to have a horizontal line after the ultimate stress. That's another common. And if I plot it, the first portion is the linear portion, which is almost a vertical line, and then I have my plasticity region is modeled here as a straight line. Then I have the third straight line, which is the constant stress. As strain increases, it helps sometimes when I have stresses above this value to have a more realistic and maybe avoid the solver to fail because it doesn't have any points above this range. So this is my bilinear or trilinear curve for the material, for my plastic material. So I will click OK, so it is created. Now I move to the sections. So in the sections, I will create the structural properties. Say if I have a shell or a membrane. Right now, I can only create solids, right? Because I don't have any shells. So let's select the parts. So solid elastic, let's call it. And for the elastic, I'm gonna pick the pin. And then OK, and a new one. And for the solid plastic. Switch my material to the plastic. Switch the material to the plastic, sorry. And I will select the plate, right? And I have my structural sections applied. In the constraints section, I can add a point spring. If I need a surface spring, if I need to add elastic supports, I can add ties, which are bonded contacts, what we call bonded contacts in SimScale, for example. When I have two assembled parts that I wanted to move bonded together, it's a type of contact that cannot separate, which is the opposite of a physical contact, which is the contact that can separate. So we wanted a rigid body for the pin. So name rigid pin, and the reference point RP1, which will be the one collecting the degrees of freedom. And for the region type, we'll just select this part. Okay, and you can see that it creates a depiction, which is like a few lines connecting the point to the solid. Now let's go to the physical contact. So to set up a physical contact in Calculix and in PrePomax, so we first create what is a surface interaction. And here I can add the behaviors or the interaction models. So the surface behavior is for the how the compliance or the no penetration condition is handled. There are different things. Friction, so the sliding, the tangential force upon the sliding, how is it modeled, and gap conductance for the thermal transfer. I will just select the hard type, which is the basic type, which it's in the background. Calculix doesn't have like a pure hard type. It just creates a linear type with a penalty method. If you know what it is. If not, then in the future we can study more in depth about physical contacts and how they work. But it's just a penalty method with a really high, really high penalty coefficient or stiffness. So this is all that I need to define right now for my surface interaction. Now I define the contact pairs, which is each pair of faces that I will define into count. So for the method surface to surface, I will just use the defaults here. So for the master region type, I can select faces here from the viewer, but right now I will use surface name and pick the master that I selected. I should have given a better name, not master, but for example, pin contact, and then I can, for example, switch this without getting confused. But let's leave it like that right now. So I assign it, I left the default values here for the method I use an adjustment size. And I just assign the master region. So what this means is that this master surface that I assign will physically interact with the slave face. And physical interact means that no penetration is allowed. They can transfer force. If they are pressed together, they can transfer the forces by minimizing the interpenetration between the two parts. But if the conditions, the deformations or the forces lead the faces to split apart, to separate, then it can also separate, right? And this is how the physical contact works, or what the model means. So I'll just save it. Now the amplitudes. So the amplitudes, what they do is to multiply the boundary conditions by a curve. And in this case, we will use it as is always recommended to apply the forces gradually in nonlinear simulation. So if I apply the load that I want to apply to this point, suddenly, then the changes in the deformations or the changes in the state of the model can be so big that the solver won't be able to found this solution because the change is too large. So our current technology of solvers, which are based, say, on the Newton-Raphson method, they always assume that the changes are small, and this is one of the reasons why it can converge to a solution, because the changes are small. But if I apply a force that will create a large change, then I can make the solver to diverge. So what we'll do here is in order to not apply the default force immediately, we will use a curve. So as a function of time, in this case, it's pseudo time. So at time 0, we will multiply the force by 0, and at time 1, we will multiply the force by 1. So if I plot this, you can see what we'll do is just ramp up the load. So I will start my load from a factor of 0, and at the time 1, I will get a factor of 1, or 100 of the full load. And then I can control by subdividing this time portion here by time variable, say in 10, in 20, in 50, in 100 points. I can make that the initial points be the initial load or the load increment to be small, and then help the solver, the numerical solver, to find the converged solution by making these changes step by step and small in smaller steps. So that's a very crucial good practice. when performing nonlinear FEA simulations. Do not apply your forces in full in one step. You can face divergence. And that is all for the, say, the general model setup. Now I create what is a step, a calculation step. So in this case, it will be a static step. PrePomax right now doesn't have dynamic steps, just static steps. For the solver, I will just pick the default. And nonlinear geometry is needed in order for the solver to, after each load step, it recomputes the model and it checks, for example, if the physical contacts are separating or what nodes are under contact after the step of the formation that we applied. On the incrementation, we will leave default. We'll use a direct incrementation, max increments, say 1000. My time period is 1 second as I define in my ramp. And my time increments, if I enter here 0.1, it means that I will have 10 steps, right? So let's leave it at 10 right now, because it looks to me that this case won't have such a large deformation, and dividing in 10 steps should be enough. Otherwise, if I face issues, I can lower this value to divide 1 second into 50 or 100, even 500 steps I have seen before. Or another thing that I can do is just leave the automatic incrementation. Then if I have some divergence, the solver will automatically cut the time increment to make the load increment to be smaller, and thus helping, in principle, helping the convergence. But I will leave these 10 steps I did in this case. It should work. It worked with my first try. Now for this step, I can define what I need. So I will first define my boundary conditions. So let's define first the symmetries. So I created a new boundary condition of displacement, and my first one will be my symmetry around X. I don't have symmetry around X, right? Around C. And then U3 would correspond to the third displacement. I will leave it at 0. And now I will just select these faces would correspond to the symmetry plane, or the plane where I cut. Okay, and new. Now the symmetry around Y. So U2 equal to 0 in these faces and in these faces. Right. So now my model, okay, and new. So my model is already constrained in the C and in the Y direction, but not in the X direction. And I know that from my physical conditions that it will be fixed at this back face. So I will just call it fix X 0 to this end face. Okay. And now my model should be mostly all fixed. I am only worried about the rigid body motions of this part. So I already fixed it in the C and Y directions. And now that I think about it, I might have induced an error here. And let's talk about that. So the problem here is that with by the physical constraint, the connection, the rigid body connection to the remote point, all of the degrees of freedom in the nodes in this part are defined by the connection or the projection with respect to the degrees of freedom of the remote point. What that means is that when I do this and I apply the condition, I create an over constraint. So I'm telling it that it won't, it cannot move here and it cannot move here, but I'm also already constraining these degrees of freedom by the remote point connections. So I'm gonna fix this. So I'm gonna just leave this and leave this one free. In this case, I need these two faces. Okay. And now I can deal with the remote point connections. So for the region type, I changed from selection to reference point name, and I have the RP1, which is the only one that I have. And this one, I wanted 0 in Y, 0 in C, and I also want 0 rotations. So the only free degree of freedom will be in the X direction where I will apply the load. And the body is rigid, so I don't have to. It won't deform, so I don't have to worry about the symmetry conditions in this case. For the loads, now I will apply my load, which will be a concentrated force on the remote point. And I input the value of the force. I want a force in the X direction. So on my original model, I entered 100 kilonewtons, but I am modeling only a quarter, right? So let's do 25 kilonewtons in the positive X direction, right? To create the uniaxial tension state. And that's it for my boundary conditions. I use the symmetries, I use the remote points, I applied the correct rotations and fixed to the rigid body motion of the rigid part, and I applied my load. I'm gonna save it quickly before going ahead. And finally, for my results, I want to have a little bit more outputs here than what it is offering. So for the elements, it is giving me the stresses, the strains, but I also want the equivalent plastic strain, which is the one that we used a moment ago at the beginning to check for the occurrence of plasticity. Okay, and I also want the contact output results, which will give me what points are under active contacts and also the contact pressure. Yes, this is what I want. I'm gonna save, and I can already start it, and it will immediately tell me if I did a mistake or it will start running. It's a little big for model. It failed, so let's say what I did. So it says error in cascade. The degree of freedom corresponding to the node 5, here's 0. In direction 2, is detected on the dependent site. So that's the error. So let's see what I did wrong here. Let me check something here. This is what happens when you do the live demonstrations. Yes. Let's switch the master and the slaves here. And that's here. It failed again with the same error, so that wasn't the issue. So let me check what I did different here. I'm so sorry. It's okay. Sorry. And the symmetry on Y is okay also. Such a weird message. The concentrated force is also on the same, in the correct direction. So let's check the message. Okay, I'm so sorry. I'm so sorry. I might have missed something here that it's not obvious to me right now. I'm so sorry. Let me double check here. If you have any questions in the meantime, we can start interacting about what we have done here. So you are not waiting there in silence. So the degree of freedom corresponding to node 5 in direction 2. So node 5 direction 2 is Y, is detected on the dependent side of a multipoint. Yeah, so the master should be the whole. Let's rename those faces so I know this book goes. So it's not master, it's just pincer. Yes, 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 yes. It's the curse of live demos. Happens every day. And this one is whole surface. That's what happens. So what is happening, what I understand that is happening here is that you cannot have the same degree of freedom constrained by two boundary conditions. So in this case, if the I am applying in the y direction, let's say this node here, I am saying that it's 0 in this direction, right? But then it is, if it's a slave of the physical contact, then it is also telling it what the deformation in that direction should be. And that's an over constraint of this node. So what should fix the error here, if I am correctly, is setting that the master surface, which is the one that won't be slave, that won't be applied, should be the whole surface and not the pin surface. So let's here, contact pair here. Okay. So the master should be the whole surface and the slave should be the pin surface, right? That should make it, otherwise I will do other change. Let's try to run again. Yes, it failed again and it says the same error, which is weird. Let's do something here because I think how it is. Let's say that this is fixed instead of 0. And let's say, because it can be that by making 0, it's not using elimination, but it is using a Lagrange multiplier, which is another concept. And that might be what is causing the over constraint. Let's try to run again. Which I think shouldn't make any difference, but all the solvers are different. So the same error. It's detected on the dependent side of. So what is node 5? Oh, I'm so sorry, I'm running out of time. And I found this error. Oh, what is that?
I think you could provide us with the final model, Guillermo, and then once you find what caused the mistake, I'll let the others know.
Yes. All right.
I think that works.
Yeah, I think that.
Probably just a small mistake, I guess.
You showed us as extra in the beginning. I'm not sure. Okay, so let's go back to the previous model, the full model, and we can check out the results. They are not available. I will need to run it again because of the way this works. It leaves it on the temp, but we can review the Gerasimov says something you showed us in the extra in the beginning, like when demonstrating the contact. Yeah, it could be. Yeah, would not have happened with SimScale. Surely, I was thinking of using SimScale. SimScale is, very, very, very robust. Not because I work there, because it's true. It's very robust and very helpful, very easy to use. Like all of these details are already taken care by us. So. Yeah, here I have these things that here I don't have the symmetry conditions, and this solver yeah, it's running right now. It should finish in a couple minutes, so we can see the results. Anyway, I'm gonna give this feedback to the people at PrePomax. So I'm gonna make them a very nice and technical question of how these boundary conditions are being handled, if they are being handled by Lagrange multipliers or they are being handled by elimination. Because I'm gonna guess that they are being applied as multipliers. That's why it's creating the over constraint. You know, we can do another one in the future and use Salome Mecha. Yeah, thank you, Yurasion. I will definitely reach out to the issue tracker and see, because I completely think that this should work. The problem is the way these symmetry boundary conditions, they are not symmetry because I am not using symmetry, use a simple displacement boundary condition set to 0. It shouldn't create an over constraint of a system of equations because it should be treated by elimination and not by Lagrange augmentation. If you know what that means, if not, yeah, we can start the implementation of FEA. There are no options here. Or I can just, say deactivate this one, and add a new just fix at the back, and it won't work, it won't be realistic, right? But it should allow me to debug a little bit. So this one completed, we can check the results again to wrap this up. And then when I have the fix, I will let you know. I will post in the site, in the Science Circle forum. So you can see here, for example, that the physical contact, it is transmitting the force. Let's check the stress, right? So let's go to yes, it's on the last step. So you can see that it is actually transmitting the force by the highest stress that we can see here. But we can see here that it is also able to split apart. So what a physical contact is, so a more realistic condition than, say, what we call a bounded contact, where it pushes this region under contact, but it will also have pulled these together, and there wouldn't there be any ovalization of the hole, as you can see here, that is happening, which is very, very, very interesting. Also, due to the mesh, I only have 2 elements, and you can see that it seems like there is like a plane of elements, but it's not real. There is not really a plane here of nodes. This is what causes a little bit of deformation to the side. So you will need here, you can see here that it is deforming a little bit. So you will need here to perform your mesh independence analysis, just refine this mesh a lot to see if this lateral displacement is real, or what is causing it. And then finally, this plastic strain field, it shows us at what point plasticity is happening, or at what point we have surpassed the yield point and we are on the plastic region. We can see here all colors above blue are happening, are under this condition. Okay, and I think it should be enough. If you have any questions, final questions, you can make them here. Thanks for your attention and your patience. Sorry for the live demo problem. It's a curse, as someone said. It happens a lot. So I will have to review and see what I missed with respect to my other models, my preparation models.
Thanks, Guillermo. Appreciate it. Any questions before I wrap it up, guys? And as you said, Guillermo, we'll wait for your feedback, and then you can just post it in the community.
Okay. Yeah, we'll post it.
That's a good plan. Cool. Any questions, guys, to Guillermo while we have him?
Any obvious limitations of PrePomax? Yeah, it has many limitations. It's under active development. Obvious, there are no dynamics. There are no dynamic analysis. So if you need to perform dynamic analysis, not yet. The meshing is, I will say, halfway. You cannot create like really nice hex meshes, even for swappable bodies. That's not possible yet. And on the structural side of things, shells are available, first and second order shells, but line elements such as beam, trusses, bars, cables are not yet available. I think those are the limitations at the top of my head right now. Can it convert also BTK or other parity? As far as I know, this results viewer is based on BTK. So sporting will be the question. I will have to find out how to do it, but I'm gonna guess that the results can be somehow exported to BTK. I just don't know, right? But from what I read, this viewer or these results, everything, also this viewer and the mesh viewer, they are all based in BTK technology, as far as I know from my research.
Right. Thank you so much, Guillermo, for your time. Really appreciate it.
Yeah, you're welcome. Welcome, everyone.
Right. Then we wrap it up, Guillermo, and then hopefully we'll have another session in the future.
Yes.
Thank you so much and enjoy your day, mate.
Okay. Goodbye, everyone.
Take care. Bye-bye.